I welcome you to Earth and Climate Sciences Deep Thought of Mimamsa 2026. My name is Shubhra.
And I'm Swastik. We are the podium coordinators for this deep thought. Before we start, we'd like to request everyone to put their phones on silent.
We'd like to first introduce the judges for this round, Dr. Ajay and Dr. Shreyas. Dr. Ajay works in geodynamics and geophysics.
And Dr. Shreyas's research lies in biogeochemistry and paleoclimatology. We thank the judges for being here with us. We request our judges to pick a chit and determine the first team to answer the question, and we'll proceed clockwise from them.
So it's IIT Madras.
So the order of the teams will be IIT Madras, IISER Bhopal, IIT Delhi and IISc. We will now start the ECS Deep Thought. The 4 questions for this round are present on the screens. IIT Madras, please select a question. Okay, so the first question is Simpleton Singleton.
Simpleton Singleton. The famous paleontologist Dr. Whipple, who has the superhuman ability to perfectly identify and classify species even from their fossils, is studying some rather interesting marine invertebrate fossils when he has the idea to plot their diversity across geological time. Dr. Whipple has also perfected the art of dating fossils accurately, and there is no scope of any bias here. Going purely by the fossil record, he gets the plot marked by the blue line in the graph, which will be shown. However, his rival Prof. Berry realizes that the fossil record is not an entirely accurate representation of the diversity of species at a given time. His studies result in a revised plot shown by the red line. The plot is as shown. Note, Dr. Whipple and Professor Berry are more concerned with accurately representing the diversity at a particular time, not the number of species alive at that time. Question 1. What are some factors that lead to the difference between Berry and Whipple's plots? Hint, notice that the bias is exaggerated near recent, 0 million years ago. Pranava, another paleobiologist, is visited by Bindu, a manifestation of the force, who tells him that both Berry and Whipple are wrong, and there is another hidden factor that is biasing the fossil record towards the recent. He hints that it has to do with singletons, species that are only found once in the fossil record. So question 2, describe how singletons could bias the fossil record towards the recent. Think about actual species duration versus recorded or observed duration. Dr. Auspicious Ra, unaware of Pranava's work, uses Berry's data to plot the origination and extinction rates across geologic time, and the plot is given as follows. Question 3. Using Dr. Ra's graph, interpret the peaks and troughs in Berry's graph. This is the end of the question. Now I would request the teams to put forward any questions or doubts that they may have. Question 2. Oh, wait. Describe how singletons could bias the fossil record towards the recent, like towards the recent time, like in this plot, towards 0 million years.
Yeah, so the recent here is towards 0 million years.
Yeah.
0 million years ago. Yeah.
Any other questions? The thinking time starts now. Participants, you have 10 minutes remaining. 5 minutes left. Two minutes remaining. Minute left. Thirty seconds left. The time is over. IIT Madras, first it's your turn. You have 5 minutes to answer. May the force be with you. And your time starts now.
Hello. So for the first question, we have three graphs. The blue and red graph are for the consideration now. The blue graph is Dr. Whipple's graph, which you can see, and the red graph is Dr. Berry's. So the first observation is the trends in both the graphs are the same, but near the recent zero, the exaggeration is more, and we can see exaggeration in different parts also. So I claim that maybe both of the profs are focused on accurately representing the diversity at a particular time. So it's basically the number of species alive at the time plus the fossil record which they have to maintain this. So if I I believe that Professor Whipple has plotted the exact raw data for the diversity at a particular time, while Professor Berry has plotted the diversity per some constant, say 10,000 species. So for that, the trends don't change. Like for a general diversity curve, which we plot for raw data versus time, we can see the trend by for inferring diversity, we'll just see the relative positions. So for both the graphs, the trend remains same. And for the first question, I think the factors are this only. And the second point, which I would like to say about the okay. So for question two, for the question one, I need to say a second point that near the recent, maybe the excavation data and the research data are not accurate, not correlating for both the profs, because obviously the fossils that came before have a much concrete data, and the fossils which came recently may have been both the profs may have different data for that, so since the research is relatively new and not concrete. For the second question, for singletons, I believe that as you can see here, we have Steno's law, like if my fossil appears in T3 and T1, then I'm assumed to believe that T2 also has the same fossil with this. So maybe if a singleton has appeared earlier, at an earlier time scale, then I'm not sure if that species still exists in the recent timeline, or maybe if a singleton appears in the recent timeline, I'm not sure whether to include that or not, or maybe that creates a bias towards the near recent because singletons are, we can't really evaluate the singleton criteria. For the third part, you can see Professor Ra's graph where we have the origination rate and the extinction rate, and the spikes in the origination and extinction rate match for the graphs. And
yeah, so the troughs we see here, these are because because when there is no peak in origination rate. So if you can see from 300 to if we go to 200 in the starting part, the origination rate is decreasing, so which is causing this trough to happen. And we can see all the peaks here are because of the peaks of origination rate. The extinction rate, so what happens when extinction rate increases is that the fossil at the time will be more, but like they will be of the same, so they will also contribute in the this peak. And the troughs here are because of the decrease in origination rate between 300 and till 200.
And here for the third green graph drawn by Professor Pranav, he exactly that this is due to the singleton species that we have a bias over here. So maybe I believe that Professor Pranav has taken into account the singleton species and not really considered the research related to that, and have considered the rest of the fossils into for his graph. So that's why the trend in all the three graphs, the peaks and troughs match, but the numbers don't exactly match due to different methods of calculating the diversity curve. So for inference, we'll have the same data, but same trends, but we don't have the same number.
Only 30 seconds left.
Like whatever points they are being marked, they are the trough points. So whenever you get a peak, you are getting after getting a peak,
the origination rate is decreasing, and because of that we are getting the trough here, this trough. and other troughs are just because of like this peak, not a trough.
Your time is up. Next up, IISER Bhopal. You have 3 minutes to present your answer. May the force be with you. Your time starts now.
Okay, for the first question, uh, the trend is something like this. For Vipul's graph, and for Berry's graph, it is almost something like this. However, this difference is pretty evident because, like, this person, the diversity is on the y-axis, and this is the time scale. So what is happening is Berry might have considered the genetic and the phylogenetic similarities as well, and which I think Dr. Vipul did not consider. So the concentration of the diversity, the difference in the concentration of the diversity is pretty evident because of that. And even the fossil record might have been more in case of the recent most excavations. So that is the thing.
Hello. For the second answer, we've considered that a singleton species is found usually in one layer. So when you go towards the center, the older sediment layers, the layers that are towards the down direction, they are older. If due to some geological processes, maybe erosion or whatever has happened, the sediment layer might have switched and creating a bias for the records.
Okay, for the third question, to interpret Berry's graph peaks via Pranav's graph. So what is here happening? What is happening here is look at the peaks of origination extension rates. They are peaking at the same time, which basically implies that the number of species diversity is
Only 1
increasing at
minute
the same
left.
time and is decreasing at the same, or is the number of species which is increased is dying. Therefore, there is a extension rate because the species which are being which are originating are also getting extended really fast. Therefore, here in the Berry's graph also, whenever there is a increase in number of species, there is after that some time there is a decrease. There is also a decrease in the number of species. That is evident from that graph, since the original rate and extension rate peak at the same time.
Less than 30 seconds left.
Peak at the same time. Further, therefore extension rate is basically the dying rate of species. So since they are peaking at the same time, therefore it's explained at the time at which in the Berry graph there is a peak, and there is also a peak and trough in the Berry's graph as well.
Time's up. IIT Delhi, you are up next. You have 2 minutes to present your answer. May the force be with you. Time starts now.
Yeah, so our supposition is that in the Whipple's and Berry's plots, they've basically taken, if you find one fossil of a particular species or you find 200 fossils of that species, they've taken it to be the same, which is why you'll notice that their graphs are like basically scaled according to the factors which the previous people had discussed, that number of fossils that survive will be a bit different, so you can do some sort of linear scaling. But it is very important to note that if you have 200 species, say constant time, then at every point of time, you will have something that survives, right? You might have 200 that survived before, but only 50 that survive now. But in each case, to diversity, they will contribute +1. But if you have a singleton found, then imagine that this was like the population graph. Then the number of fossils surviving graph will be something like this, because in recent times, there will be less decay, so they will survive more. So when you sample from this exactly one fossil, it is more likely to be nearer.
Only 1 minute left.
It is more likely to be recent than it is to its actual representation, which was throughout. So you will need to factor in the number of graphs. And when you do that, you will smooth out the curve a lot because you will let go of simpletons. So this is our answer to how singletons affect it. And the factors that lead to difference between Berry and Whipple's plots are, again, erosion, etc. For 3,
Yeah, for the first one, tilting might also be there, but not sure. For the third one, we can see that at points in
Less
most
than
cases,
30 seconds
the
left.
origination rate is greater than the extinction rate. So there's an continuous rise. But there are points where the extinction rate suddenly rises at peak, and corresponding to that, you can clearly see a sudden trough in the graphs of the that we get of the number of seeds, that diversity graph, and they correspond to the points where extinction rate massively exceeds origination.
Time's up. IISc, you have 2 minutes to present your answer. May the force be with you. Your time starts now.
Hello. For the third part, we see seven peaks dots corresponding to points in time where extinction happened and then origination happened after that. And Berry's curve, we also see a curve at similar time frames. So that indicates that every time whenever there is an extinction species, there is a sudden drop in the number of species of fossil according to Dr. People, and that can be seen in the graph. One more thing that is of interest is that there are two peaks between 400 to 300 and 200 to 100 million years ago that are not present in Dr. Anava's curve. And if you look at the curve by auspicious era, then those correspond to peaks
Only 1
of
minute left.
origination and extinction rate that are nearly coincident. So there is one peak of origination and extinction that are nearly coincident between 400 to 300 and 200 to 100, and I believe that shows that in the same time period, while the number of species, while the actual number might not have changed because origination and extinction happened at the same time, the number of fossils that were found in time increased. Even though the actual number of
Only
species that
30
were
seconds
present
left.
coincidentally were not present.
For the second part, we can explain the singleton causing the bias in two ways. First of all, there's the accumulation. If the singleton is not destroyed but get accumulated, there will be a lot of bias. The differences can be in 400 to 300, and especially at the end. And second is, of course, the time period as well, if it is very recent.
Yeah. First part, we agree with the IISER Bhopal solution. The number of species that are being recorded or preserved will be larger at the end.
Time's up. Judges, do you have any questions for the teams? No questions?
Questions, Team Madras, on the second part of their question.
Yeah.
So it wasn't clear to me, how are you?
So like if a singleton species occurs in the near recent, said that the mapping, like the research on that may not have been proper, or like to include that in my diversity, that would create a bias. Or if in the second case was, if my singleton has occurred at a larger period earlier, then I'm not sure if that singleton species has become an extinct before my recent timeline, or it's still a part of my diversity. So.
Okay. The answer for your
That the points in the third graph which you are given, or rather the second graph which you are given, the peaks where the extinction rate increases, is very much larger than the origination rate, corresponds to the points where we see a massive drop in the diversities of the species. And other than those points, we see a constant. The origination rate is greater than the extinction rate in general for the points where there are no peaks. So that's where there's a constant increase. And yeah. So that's how Dr. R's graph spreads the peaks and troughs of Barry's graph.
Yeah, maybe just last one to Bhopal. So you, to IISER Bhopal, on the first part of your question, you were discussing, you were invoking the genetic level identification of these species. So do you think it can be done with the fossil record?
Usually I believe that Vipul only considered the morphological or aspects of the fossil record, but maybe there was Dr. Berry even included not only the fossil record but also the phylogenetic correlation. Like he might have read the phylogenetic trees and then he might have correlated the species with that.
Think that that would decrease the number of species?
The decrease is denoted by like the closeness of the species, like how related two species are. So Vipul might have plotted them in a different manner, but then Berry might have concised them into a smaller, into the same.
Thank you.
I have a question to IIT Madras. It's more of a clarification. You guys said that if you remove singletons, that Pranava had removed singletons in his graph, why would the drop in that case be greater near recent as compared to earlier times?
So it's the green graph,
Yeah.
you're saying the drop near the recent means this drop between 300 to 0?
No, 200 to 100 to 0.
Okay, so the plot, the number of species, why it should be less than the red and blue plots?
Why is the drop there greater than in other places? You're saying we have removed singletons, right, across the board. Why is the drop at the end greater than the drop at other places? Like, where is the drop near recent?
So like answering for the second question, I may not have considered this part, but if I may have considered third part. I just saw the like bias which singleton may have created and presented an argument.
Just a short follow-up. I believe you have trouble understanding what I'm trying to ask. I'm trying to ask why the bias that you're considering because of the singletons, it should be greater near as compared to back in time.
Okay. So I think because the earlier fossils, due to sedimentation or maybe erosion, may have tampered. So, like my argument was based on the research on singleton species. So I think if singleton species occurs only one time in the entire timeline, then I'm not sure if that should include in my diversity or not. So.
No further questions?
No, I have a question for IISc. For part 2, you guys said that it had something to do with the accumulation of singletons. Is that what you said? Where in time are these singletons accumulating for this, your answer to be true?
So, what do you mean by where in time are the singletons accumulating?
What?
The point is that singletons, whenever they are being recorded, the question is like if we are adding them to our total count or not. So that is essentially considering two factors. Firstly, so if you're saying that the first two graphs have just added them to the total count and the other one has not. Other factor is that the recent seeing the two effects that is causing this. So the other effect is that the number of species in recent years will be preserved more. So yeah. The number of species in recent years will be preserved more, so there's a bias towards recent years where, yes, so there's a total bias towards the species being recorded in recent years.
Now I request someone from the question making team to explain the answer.
So for one, the factors that could lead to some differences between the plots between Berry and Whipple is something to do with the fact that modern fossils, or like recent fossils, say from 50 million years ago, are going to be preserved much better. You're going to have many more of them. And also that you have comparatively less amount of older rocks. So even the fossils that were formed at old times, say 500 million years, they're going to get destroyed a lot over time. So you're just going to have just a lot more volume of fossils towards the recent, say, 100 million years to 0 million years, which is why you see a much more biased fossil record towards the recent compared to the past. Also, you guys said, I think, phylogenetic stuff, genetic data or like DNA does not usually get preserved past like even 1,000 years, 10,000 years, maybe a million years at most. So over geologic time, genetic data, phylogenetic classification is going to be pretty sketchy at best. Now how singletons are going to bias the fossil record is that you're going to have more singletons in older times. Because again, the fossil record is poor, so the chances of the multiple occurrences of fossils over time is going to get destroyed. So it's more likely that you'll have more singletons in older times, and you're going to reject all those because you're not sure when those fossils actually originate and when they end, so there's no point counting them. And now when you remove them from the old times, preferentially because there's more of them, like a frequency, they're occurring at a higher frequency in the older times, you're going to be decreasing your sample size of the older time. And if you will refer to the brief, we said that to compare diversity, you need to have samples of the same size. So you already have a larger sample from the modern recent time. You're going to have to scale that sample down to a lot, which is why you'll have a much bigger drop from the red graph to the green graph near the recent. Question 3, you're expected to notice that not all of the peaks are concurrent, as in the peak just before 300 and the peak at like 150, they have origination and extinction peaking at the same time. All other peaks have extinctions peaking first and then originations peaking after that, immediately after that. So those represent mass extinction events, the 5 of them that have extinctions peaking first. A lot of animals, species are dying out at the same time. And then because now there is not much competition, there's a lot of new biological niches opened up, there's going to be a boom of species of sorts. And the 2 times when the peaks are at the same time, that is because it was a time of exceptional preservation. You found like a lot of very well preserved species. You found a lot of singletons. And that's why you don't see the 2 spikes in the green graph. Yeah, thank you.
IISER Bhopal, which question would you like to choose? Okay, sorry. Do any of the teams have any questions for the QMCs, any clarifications? None? Okay, so we'll move on. IISER Bhopal, what question would you like to pick? Okay. Okay, so there are 2 tides a day, right? Amun, an evil scientist cum dictator, the ruler of Montreal, in their quest for world domination, hatches a plan to invade a neighboring island country, Ewok. However, there is one big problem. You see, Ewok is only connected to the mainland during low tides. The low-lying isthmus between Montreal and Ewok is submerged underwater during high tide. All of Amun's ships are busy enforcing a naval blockade on Ewok, and hence Amun has no choice but to invade only during the low tide when their armies can march over their land into Ewok. Amun's army generals tell them that they need an invasion window of at least 12 hours to be able to conquer Ewok. If the tide comes back before 12 hours, the invasion would be an abject failure, just like Amun's attempt to develop their own country, Montreal, into a happy place instead of having to declare unnecessary wars to support their fascist regime. Amun, therefore, is in desperate need of a way to be able to predict tide timings accurately. Aman knows that tides due to the moon are much stronger than the solar tides, which can be ignored. Aman also knows that the moon causes high tides on the side of the earth that is facing the moon, as well as the side that is opposite to the moon, which means that one day we'll have two high tides and two low tides. Therefore, the low tide should theoretically last only 6 hours, which is not enough time to conquer Ewok. The text in yellow on the graph says land bridge, and the text in blue above in the positive says no land bridge, just to clarify. And the text in red says invasion window, that is the ideal time. Disheartened but not defeated, Aman makes some on-ground observations of the isthmus to verify their calculations. To their merry surprise, they find that the tides somehow transition from 2 highs and 2 lows per day to only 1 high and 1 low per day in a matter of days, allowing them to invade Ewok. Explain this phenomenon. Assumptions. This phenomenon has nothing to do with the sun. It would happen in a two-body system as well. You can assume the seas to be of endless depth such that the arrangement of the continents and the shapes of the ocean basins don't affect the tides. That is, this phenomenon would happen on a planet that is completely covered by oceans as well. You know that the moon causes high tides on both sides of Earth, the one facing it and the one opposite to it. You can assume the moon's orbital period around the Earth to be around 28 days. If the angle between the moon's orbital plane around the Earth and the Earth's equatorial plane is 30 degrees, what is the latitudinal boundary between places having 2 tides a day and places that have only 1 tide a day? How does this boundary change throughout the lunar month? Will there be a region that permanently gets 2 tides a day? Will there be a region that permanently gets 1 tide a day? Hint. Think about how the distance between the moon and the equatorial plane of the Earth changes through the lunar month. The same assumptions as in the previous question apply. Delighted by their country's new tidal discoveries, the scientists at SANA, wannabe NASA, try to figure out whether closed basins like lakes can have tides. Two prominent scientists in the organization, Agastya and Swastik, are engaged in a heated debate. Agastya says that since lakes are closed bodies, nothing can supply water to them, so their water levels cannot increase. Swastik, on the other hand, argues if one were to imagine an earth with only land except for one lake, then keep on increasing the diameter of the lake, it would eventually become an ocean, and the continent would in fact become an island. Therefore, Swastik says there is no distinction between a lake and an ocean. Give your views on this debate. Can you think of a way to reconcile both of their arguments? To test their theories out, they dig a giant circular hole in the ground, entirely in the northern hemisphere, thousands of kilometers in diameter, and fill it with water, basically creating a giant circular lake that is not connected to the oceans. Now imagine a tidal wave in this lake. Remember that given the system's large horizontal scale and the slow tides, the Coriolis force is important. Explain what kind of tidal motions would be observed in this lake. How would a similar lake in the southern hemisphere differ? Do the participants have any clarifications on the question? Okay, if not, then we'll start the thinking time. Your time starts now. You have 15 minutes. You have 10 minutes remaining. You have 5 minutes remaining. Two minutes remaining. One minute remaining. Thirty seconds. Time's up. IISER Bhopal, you have 5 minutes to present. Your time starts now.
This is a point here and this is a point here. Okay, so in the first question, in certain days, the tide shift from 2-day tide to 1-day tide. What happens is, since the moon, right now, these 2 points are these are the same side to the moon, and this is the point is away from the moon. What happens is, when the moon rotates along with Earth's rotation, what happens is that this point, which rotates relative to the moon, when it comes back, when it rotates along with Earth, like it goes along the Earth axis and comes here, and the moon is also rotating. This point is no longer in the opposite side of the Earth with respect to the moon in certain days. So therefore, since the moon causes tidal waves in the points facing the moon and the opposite point, since this point is no longer in the opposite tide, the high tide is not experienced in that point. Therefore, only one during a day, because during a day the point moves from this point to this point and back there. So therefore, during a day only one high tide and one low tide is done, and this is done in a particular time frame in a month. Therefore, in a few days, there will be a chance of a 12-hour period for high tide and low tide. Now, when we come to second question, which is two tides a day, and will there be region which permanently gets one tide a day is the North Pole and South Pole. These regions will get permanently one tide a day. Why? Since this is because these regions will only be in the one side of moon with relative to the moon. Therefore, they will experience only one tide a day. Also, so how does the boundary change throughout the lunar month? This boundary changes, like this is the region of height, the level of tide. This is the level of tide. There is low high tide. There is high tide. With respect to time, this area gets shifted upward slightly.
For the third question, we can see when for a lake, the conditions for a lake and an ocean are not usually similar. The depth profiles or density profiles are different.
2 minutes left.
And when there is no inflow of water, the depth would gradually decrease and on increasing the diameter. So all of these parameters would change.
In the last question, when the moon will come, when the moon will be near to the north polar side, since the lake we are creating has a thousands of kilometer diameter, so it will face the tides in the almost half part when the moon is closer, and the south pole will be in the other half part when the moon is closer. The won't face the tides, only the half circular portion will face the tides. Since it is in thousands of kilometers, it will act like similar to sea. Not exactly, it is very large lake, but a little similar to the sea, and the tides direction will be opposite.
Okay, we can restart the timer. IIT Delhi, you have 3 minutes to present. And your time starts now.
Hello. So first we'll start with part 3. So basically the size of the lake will depend, the formation of tide will depend on the size of the lake as it gets relative to the curvature of the earth. as the size increases of the lake and gets relative to the curvature of the, that is the radius of the earth, tidal force will become more apparent. So the tides are caused due to the differential force of moon from the center of the earth to the point at the to the point we are considering. So the force is 2 gmm by r cube times the 2 gmm by r cube times the radius of earth. So the force is maximum at this point, becomes 0 at this point relative to this point. So if you have a lake, say at this point, all the water is being pulled upwards. So obviously all the water can't simply go upwards. So there's no actual tide being formed here. But as the lake gets bigger, the force here is lower, but there's a tangential component that is pushing the water here, and this water is getting pulled upwards. So all the water gets concentrated upwards, and hence tide will be formed here, of course. And similarly, as you increase, the effect gets more apparent. So this is diagram for the fourth case.
So in the last question, we can clearly see when at a certain time for the northern hemisphere, the moon will pull the tides of the lake in the same direction as it will, as the Coriolis force will deflect it. For if the moon is on the opposite side in that part of the lunar cycle, the Coriolis force and the gravitational pull of the moon will cancel out each other, and tides will not be formed.
For the second question, I claim that, for example, consider the moon at two positions. The first is when it is in front of the earth, in the sense that if this is the axis, then the earth is over here. In this case, let us assume that the region of high tide formation is this. It will be with respect to the location of the moon, not with respect to the rotation of the earth. So in this case, if you consider this particular circle, it does not really go into the high tide region. And instead it remains like very roughly at a constant difference, constant distance from the moon without much variation in ratio. Whereas when the moon is, say, over here, facing it head on, then even for the these edges, the difference when they're pointing towards the moon and when they are exactly on this great circle, or exactly in the middle, then that is more. Because this is not high tide at all, and this is still some amount of high tide. That is why there is a variation. I don't think there is any place that will have only one tide a day, because
your time is up.
At this point of time.
IISc, you have 2 minutes to present. Your time starts now.
Hello. For the third part, the debate between Agastya and Swastik, our answer is that there will be, if the lake is small, the quantity of water in it will be low, so you might have some tidal effects, some increase of water somewhere and some decrease of water in other parts of the lake due to something similar to tide, but that would be very minuscule, and it would probably be negligible as compared to the surface waves on the lake, so we don't really clearly see any such effects on regular lakes. As you increase the size, as Swastik says, as you increase the size of the lake, the quantity of water will increase, and so the impact that tide has begins to increase as compared to the surface waves. It becomes less negligible and more comparable, and even eventually surpassing the surface waves.
1 minute left.
For the second part, we can say the one that directly falling with the 30-degree latitude would have the two high tide and low tide. The one that is exactly 90 degree, that would have one high tide and one low, and these are the places where we are exactly permanent to high tide to low tide. And yes, the answer. And through the lunar motion, the two high tide, two low tide become one high tide, but the one high tide, one low tide will never change.
So fourth part, it is, we are adding on to IT Delhi's portion. Okay, so during the North Pole, we will observe that at first there will be a rise that will come, but then due to the, firstly the size is sufficient enough that the gravitational difference is there between the center and the portion away from it due to the radius. Then due to the Coriolis effect, it will move rightwards and it will whirl rightwards, and over here it will whirl leftwards in the opposite direction. Yeah, that's it.
Your time is up. IIT Madras, you have 2 minutes to present. Your time starts now.
Yeah, so the first question to explain the phenomena, so that can be explained when I draw the diagram for the question. So as we know, the moon is at some angle with Earth. So what I'm assuming is, so we know it's given that the moon angle is at the angle of moon orbit is 30 degree. So the moon, I am considering the angle of moon with the equatorial plane at any point in the orbit. So I'm considering this to be x. So this 40 on this day when the angle is x degree. Now, what we get is minus 45 plus x to 45 minus x.
1 minute.
This is the time for which this is the angle for which we get this high tide, and both only permanently 2 tides we are getting. So when you check x from minus 30 degree to 30 degree and take the intersection, what we get is minus 15 to 15 and minus 90 to minus 70 and 75 to 90. This is 1 tide permanently. This is for 2 tide.
For the fourth question, we have the argument that in the northern hemisphere the Coriolis forces are towards the right. So the ripple formation which we have in the third question will be towards the deflected towards the right like a wavefront, and for the southern hemisphere it's to the left.
The judges, do you have any questions for any of the teams?
A bit confused which question they answered, which they didn't. So I'll first go for Bhopal. Can you tell me which questions you answered, which you didn't?
We answered first question, which states that explain this phenomena when it changes from two tides to 1 tide a day. This.
Okay, that's it, right?
I mean, no. We also gave what is the latitudinal boundary between having 2 tides a day, and you also gave how will this change with lunar cycle, and what will be the permanent if there exists a permanent 2 tides a day and a 1 tide a day. There exists a region which has permanently 2 tides a day or permanently 1 tides a day. And further, we also said, can you give your views on this, debate, and explain what kind of total motion is observed in the lake, in the big lake. We have answered third question.
Just a request that the one who's speaking should state or write what question they're answering, okay? Because we see a lot of stuff happening on the board where some people are moving, they're writing, some people are speaking. So please be a bit coordinated, okay? Thank you.
Are there any more questions? Okay, I call upon the question maker.
IIT Madras,
sorry.
first question I didn't get what exactly you said.
The first question, like if the second question we solve, we can...
You are saying from 70 to 90 there will be only 1 tide, is
it's
it?
a 75.
The 70 is written there. 70 to 90 there will be only 1 tide, is it?
I'm saying permanently 1 tide for the second. It's for the second part. This. It was asked that region that permanently gets 2 tide and region that permanently gets 1 tide.
So what is that number? Permanently get 1 tide? 70 to 90.
Minus it's like
70 to 90.
It's like minus 90 to minus 75 and 75 to 90. There's some error. Like I just.
Okay.
Okay, are there any more questions?
ISC Bangalore, I didn't quite get your answer for the second question. What regions did you say will have permanent two tides?
See, the the 30 degree where the moon is directly facing or oppositely facing, they will have two high tide, two low tide. The one that is 90 degree, just like in Earth, the equatorial plane, just like the polar plane is 90 degrees, similarly the 90 degree to the rotation, that will have one high tide, one low tide. That's what I denoted by that 30 and 60. That is just from the equatorial plane angle measure.
IISER Bhopal. So your answer to the third part, you just said that there will be changes in the water level or something. You just said that the factors affecting the tides would change. How exactly would they change?
You didn't give the answer for that. You just stated the facts, but you didn't give the answer whether it will have effect or not.
These conditions will be different for the lake and for the ocean. So it will be different for both of them.
Yeah, different how? That's the question.
Like it would affect the oceans in much different, like the tides would be there in the oceans, but it wouldn't work similarly for the lakes. No tides.
I call upon the question maker to give the solution.
So for the first question, how this happens is, let's say this is the Earth, these are the poles, so this is the equator, and this is your equatorial plane. Now you have been told that the moon's orbit is at an angle of 30 degrees with the Earth's equatorial plane. So let's say the moon is somewhere here in its orbit. So at this point in the orbit, the tides will be something like this. Right, there will be one bulge towards the moon and one bulge opposite to the moon. And this would be an ellipsoid. So this is a 3D ellipsoid with stretched on the axis. That is the line between the Earth's center and the moon. So in this case, what you have is let's imagine somebody is standing on the equator. A person is standing on the equator. They start out with high tide. They rotate till here, they get a low tide. Go back, they get high tide, low tide, and then come back, high tide, 2 tides a day. But for someone standing somewhere over here, so this point is getting the least tides. This is the lowest of all the lows right here. And as this person rotates with the Earth, the tides can only increase from here, right? So for this person, they are already at the lowest low. The tides keep on increasing till this point and keep on decreasing till this point. So that is how that happens. And the boundary for this effect will be this is 30, so this will happen till 60. So 60 degrees, anything that is north of 60 degrees will get one tide, and anything that is same for the southern hemisphere. And since the moon is rotating, at some point it will come in the plane of the Earth's rotation. So somewhere over here. Now, everywhere, all places will get two tides when the moon is in Earth's equatorial plane, right? So there is no place that only gets, that permanently gets one tide. And then the last question is about the lakes. So, so I think two of the teams got this right. So what will happen is, since the lake is a closed basin, nothing is providing water to it, unlike the ocean. So the lake's surface will get depressed at some points, and it will bulge out at some points. So this is how the lake gets tides. But the problem is, this bulge will be very, very small because the lake is small compared to the oceanic tides. And for the last question, so let's say this is the Earth, the poles, equator, and let's say this is your lake. So the lake will have tides something like, let's say the moon is out of the boat somewhere here. So the tides will be bulging out on this side. Right, there will be a high tide at this part and a low tide over here. And now as the moon moves away from the lake, or rather the Earth rotates away from the moon, the force that was keeping this water over here has just released itself. So something that was pulling the water over here is not pulling it anymore. So this water will start flowing downhill, will start flowing back. But while flowing back here, it will get deflected due to the Coriolis force to its right, and the bulge will travel here. And now again it wants to go downhill, but Coriolis force pushes it to the right, so the bulge goes here. Same thing happens. So basically this bulge keeps rotating in the lake. So what you get is a wave that rotates in the lake. So you get something like a bucket of water, and you have rotated the bucket of water, and the wave is moving around. And this will happen in lakes of all size. So theoretically, even a water bottle can have tides, but minimal. So interesting fact is the Great Lakes in America, they are large enough to get tides, and they get about 5 centimeters of tide, but obviously the surface waves are much, due to the wind and all, they are much larger than the tides, so you can't notice them.
Do any of the participants have questions for the question maker? No doubts? Okay, we'll move on.
Thank you, Raj. But irrespective of what you said, my argument still holds. Now, moving on to the next question. Next up is IIT Delhi. I'll just plug it in. I request IIT Delhi to choose a question. The only available questions are, I think this forest is rotten right to the core, and Pankha. Pankha? So, Pankha. Professor Soranos' trip to Norway was full of breathtaking geologic marvels. Mountain peaks of up to 1800 meter, rolling plot chalks, glacial cirques, large valleys and deep fjords. The rocks in the region had beautiful striated patterns characteristic of gneiss dating all the way back to pre-Cambrian times. Being a person of the scientific cloth, however, he could not ignore the varying types of sedimentary deposits he encountered at the foothills of the mountains. Based on simple empirical observations, he classified these into two categories, M and P. M-type deposits had large, flat, fan-shaped structures and were found near highly vegetated mountains with gentler slopes and rivers. Type P, on the other hand, had conical shapes and were found near mountains with steep slopes and sparse vegetation. Type M fans had a greater radius than type P fans, and the size of sediments contained within was generally smaller than type P, though both contained a large number of rocks which had negative values on the phi scale. The values were more negative in case of type P. The apex of the former was also situated closer to the base of the mountain in contrast to type P, which seemed to start much higher on the surrounding mountains. The deposits in type M fans were often rich in a muddy matrix and microbial and plant life, often having clay-like characters. Type P fans, on the other hand, were dry, class supported, and adjoining mountains had large craters. These are the examples of type M and type P fans. This is a schematic representing the axis of a fan. Question 1 is, after careful analysis of a few fans of both types, Professor Schoroner realized that most type P fans had smaller class toward the apex, which got progressively larger towards the toes. Type M, on the other hand, had the opposite pattern, suggest a deposition mechanism which would cause this to happen. Can you also predict what the vertical cross-sectional grading would look like in both cases? Question 2. In particularly snowy mountains containing wet, slush-like ice, the class in type P fans had relatively rounded ellipsoidal shapes with a well-defined major and minor axis. Professor Schoroner realized that this was more common for rocks near the apex of a fan. What could cause such regularity to arise near the apex? Present a schematic of how the fabric general alignment of class would look like on moving from apex to the toes of a fan. Even verbal answers giving a general overview of the fabric would work. This is a schematic of an ellipsoidal clast in arbitrary bedding plane. Question 3. Look at the example of type M fan given below. It is situated near the base of a mountain with many seasonal drainages. How does the distinct pattern of markings on the fan surface arise? Question 4. In some type P fans, the trend of clast coastening towards toes is interrupted by larger clasts positioned near the apex. These special fans, labeled type P star, share all other features with type P fans. Can you suggest a history or mechanism of deposition which would cause such a situation to arise? Put funda. This is the end of the question. I would like to ask the participants if they have any doubts.
Clasts are just broken up pieces of rock. Okay, so the phi scale is you take a piece of rock, you give it a radius, and then you measure minus log to the base 2 of the radius, and that's the phi scale.
No more questions? Your thinking time starts now. Only 10 minutes left. Only 5 minutes remaining. One minute left. Less than 30 seconds remaining. Time's up. IIT Delhi, you have 5 minutes to present your answer and your time starts now.
So, as we know that M is formed when there are gentler rivers and P is formed when there are faster rivers. So, the deposition pattern which explains all of these things is that assume that you have a slower flow, right? So it's able, so even if it has, these are for third and fourth question. So even if there are small sediments that are getting carried alongside, they will start to get deposited because as opposed to P when all the small sediments will just get carried away. So the small sediments which are getting deposited will over time vary the flow of the river, and that's why when the stream is slowly coming down, it will get deposited near the apex of the mountain, and over time that deposition will grow and grow and grow, keeping near the apex. Whereas in the case of P, since it is going very fast, it will get drawn number one farther away from the mountain, and number two it will be in a straight line, which is the direction of the river, instead of changing the direction of the river over time and being a more circular thing. These are important for question 1, and we claim that this normal grading will happen for M. Yeah, this is for M and this is for P.
So question 2, we're tasked with explaining what can cause regularity in the rocks near the apex for P-type. So you observe when the river starts near the apex, it has a lot of sediments, and the flow of the river will be granular, which corresponds to laminar flow. So when the flow is laminar, the water is moving in a predictable pattern, which causes it to polish the rocks, making them more ellipsoidal in shape. Versus near the toe of the fan, it deposits a lot of the sediment. So that causes the flow to transition into fluidal, which is turbulent. Turbulent flow will erode the rocks and weather them in unpredictable ways. So it will remove the roundness we find near the apex of the river flow.
For the third question, we can say that as it is a M-type fan, it has smaller rocks, so it is carrying rocks. So if there are any big rocks present near the toe of the fan, the water will change its path accordingly and form distinct channels and path and will flow through them. Thus all the distributaries will together form a distinct type of fan type structure. For the fourth part, we can say that initially, if there was a P-type fan that had an apex and a toe, but for some reason, if the river continued to flow and such that the toe of the older fan became the toe of the older grading profile became the apex for the newer flow, the river will continue to flow from there and will reach to another toe in such a way we can clearly see that the grading profile will just change from P to P star in such cases. So we effectively just see that the grading profile has converted from P to P star.
In question 2, adding on a few points, the general alignment of the clasts. So we predict near the apex, the clast will be aligned roughly in the direction of the river flow, and near the toe, they'll be more horizontal and randomly oriented. That is mainly because of the reasoning of the laminar flow and turbulent flow were given in the first part of the second subpart. And some reasoning behind why we have selected normal grading for M and reverse grading for P. So as the flow for P is faster, it will carry both larger sediments and smaller sediments. But due to the speed, it won't be able to deposit the smaller sediments. So we predict it will deposit mainly the larger sediments. Versus for M, as the slope is much more relaxed, it will first of all carry less of the larger sediments and also deposit the smaller sediments without eroding as much as in the case for the P-type fans. So that is the reasoning why we selected normal for M and reverse for P.
We also notice that P is breaking away chunks of the mountain as written in the fourth point. So those chunks of the mountain over time, as the river is getting
30 seconds remaining.
Slope is getting steeper, it will break off bigger portions which will deposit on the upper, which also matches with the lower 5 values for P. We are done for all the parts. Yeah.
All right. Can we restart the timer for 3 minutes for IISc? IISc, you have 3 minutes to present your answer, and your time starts now.
Okay, so for the first question, it is said that for the P type, it's the sediments, I mean the rocks are like smaller at the top and larger at the bottom. This is because the flow is faster, and because of because the flow is faster, there's more collision, and the larger rocks get deposited first because of the because it's the drag is larger, and as the larger rocks are deposited, the smaller rocks are like obstructed by the larger ones, so they get deposited at the top. So that's like the normal grading there, and the reverse grading is due to because the slope is lesser, and it's more like the flow is slower, and there's more trees, right? So the obstruction of the larger rocks is more. The smaller rocks don't get as much, and the larger rocks get stopped first, and the smaller rocks get stopped later on. So yeah, and yeah, that's it. And second part, the second part. So for the second part, it's said that because of the slush, somehow there's an ellipsoid shape, and this is probably because the slush is getting grazed upon the rocks, and it's kind of like deforming it and forming a ellipsoid shape. And this shape is more aligned with the flow, like more aligned along with the flow at the lower parts of the cone than at the top. So it's more embedded at the top because the flow is faster as it's going down. So yeah, that's that. Third part.
1 minute remaining.
For the third part is explained here, due to the fast flowing rivers, there are deposits at only certain types of M because they are so fast flowing, leaving the remaining leftover regions as a troughs. So that explains the third part.
Third part. What? Third part you have explained. Yeah, I have explained. Okay. We have 40 seconds. Fourth part. So fourth part, one factor might be that this might have to do with the shape of the mountain
remaining.
and yeah. Okay, this might have to do with the shape of the mountain and how it has changed with respect to time. So it might have been steeper earlier, and then it might have changed later. So that would have led to first M type being formed and then a P type.
And also I want to say one more thing for the first part. For the P type, the flow is faster, so there's more collision. And because of the collision of the larger, smaller rocks with the larger rocks.
Your answer.
For the P type and M fan, I believe my argument can be stated with P types being dry, class supported, and adjoining mountains containing large craters. So maybe the wind erosion causes the adjoining mountains to have craters, and the particles, the rocks breaking on the slopes and being deposited as the mountains have steep slope also. For the M type, I believe that the rivers bring along with them the sediments, and hence the M type also has muddy matrix and microbial and plant life as well. So for the grading, I would like to say that M type has rivers which bring along the sediment. So there will be a normal grading for the second, and since the sediments are deposited over time. And for P type, it is like the winds break the rocks,
1 minute
and
remaining.
smaller clasts come to the bottom, and the mountains, like the reverse grading happens.
Okay, for question 2, I would like to add on to IIT Delhi's thing. I personally believe that reason the class are more like ellipsoid and like properly shaped is because of landslides that are usually common in snowy mountains. I believe the landslide would cause way more erosion than a normal rocky erosion or like river erosion. So like that is one point I would like
30
to add.
seconds remaining.
And third question, I believe like these distinct patterns form because of like the rivers that are usually found in like M-type is found in vegetations, and their rivers are there which are like little gentler, and they'll just like sediment nearby them which will cause the thing.
For the fourth question, I believe that the irregular mountains cause this since we have irregularity in mountains, the smaller fragments are the...
Time's up. IISER Bhopal, you are up next. You have 2 minutes to present your answer and your time starts now.
We have considered that because there is larger vegetation near the foothills of the apex, foothills of the fans, that is why there would be higher moisture also in the soil. When the sediments must have deposited, the muddy soil must have formed a layer over the sediments and increased the radius of
1 minute
the
remaining.
sediments down the hill.
For the third part, what will happen is first since in top there are big rocks in M type. The M type has big rocks, so there will be a spreading of the drainage system, and when they come downwards, what will happen is since
30 seconds remaining.
the size of rocks decreases and the volume the water will be can easily the drainage system can easily erode these small rocks. They have small grains. Therefore, they will converge in the end. Since they will converge in the end, and they will form instead of multiple drains, they will form combine together and form one or two drains because of the volume of water, and the water is easily.
Time's up. I would like to ask the judges if they have any questions for the teams.
Team IISER Bhopal, what was the final answer to your question? Question 1.
Final answer was
No, the final answer was like similar to the IIT Madras, the M type and P type. We just added an extra point about the vegetation and soil moisture that would create an extra layer over the sediments.
I have a few questions. It's for IIT Delhi and IISc. So you think both of these fans were caused by river deposits, right? Both of the teams. Like both of these were river deposited. One was just a faster flowing river and the other was a slower river. Is that your answer? Question 1.
I think that was part of the question. The last line of the question, the first paragraph says he couldn't ignore the various type of sedimentary deposits, though. I thought that was something we had to assume regarding these.
The question asks you for a deposition mechanism for type P and type M fans, right? What deposition mechanism did you suggest for type P and type M fans? That's all I'm asking.
We were initially considering that P was not a deposit at all, but rather like a result of erosion. But then we read this line that they are both sedimentary deposit, and we suggested that because of that, the difference is that M is by the slower moving rivers and P is by the faster moving rivers.
That is your answer?
Yes.
Okay. Is that the same answer you guys said?
Sir, was depositions, because if you were to read the paragraph, it was said that it had gentler slopes and more vegetated mountains, and there the deposits are usually higher, so that is why.
So slower rivers type M and faster rivers type P.
Yes. Yes.
Okay.
The vegetation is also the map.
Any more questions?
Yeah, what reason did you guys give for the IIT Delhi? What reason did you give for the normal and reverse gradings?
So we mainly based our classification on the river speeds. So we think in the M-type rivers where we have gentler slopes, we have slower rivers, and they'll deposit the smaller sediments they carry in them. Versus for P-type fan, because the streams are faster because of the steeper slopes, they will firstly carry larger sediments and also deposit them, but they won't deposit smaller sediments because the river is moving so fast.
I also said that over time, because since P is eroding the mountain more towards the lower sides, it's going, as was also supported by P is in the steeper mountains. So if it gets steeper and the speed gets slower, speed gets faster, it will deposit the large ones later in time, and therefore they will be above.
I have a question for IISER Bhopal. For answer 3 in the figure, which direction are you considering uphill and downhill?
The basically in the figure which is given, basically in the figure which is given to us, the top layer is considered like the top of the mountain, and the below one is considered lower.
Last question to IIT Madras. You guys said that there are landslides, and the landslides are making the clasts more ellipsoidal, right? Why is that?
Because I believe landslides exert more force on the rocks on the apex and the upper, not the base, but more force from there as well, which that force will shape them into a smoother or ellipsoidal is what I believe.
You don't have a reason for why particularly this shape is ellipsoidal?
No, this is just my belief.
Okay.
Now I would like to request someone from the question making team to provide the answer.
Okay, so you had been given two types of fans, type P fans and type M fans. I'd like to go back a little bit to the participant brief where I mentioned that you really need to consider the surroundings for a given object in order to determine its transport history. It had been explicitly mentioned that type P fans are found in dry surroundings as compared to type M fans. So type P fans were deposited through a purely gravitationally driven process. So basically, I'll keep this with you. Basically, you have this hill slope. There's a catastrophic failure some point up the hill slope, which is what I believe IIT Madras had said. There's a landslide. That landslide causes this entire mass to get deposited downhill in the shape of a fan using a purely gravitational process, right? That is where you get drier, clasts. And then, because this is a purely gravitationally driven process, the bigger class would obviously roll down further than the smaller class. And that is why you get bigger class at the bottom, like near the toes, and smaller class uphill, okay? Why the other way is true for type M fans is because it's a river in deposit. So you have a river that is flowing. Now the rivers, a lot of the teams said it correctly, the slope will keep getting gentler downhill, right? So now
stream is losing its power to carry these sediments. And as it loses its power to carry these sediments, it will carry the smaller class further than it will carry the bigger clasts. So that was the answer to the first part. About the vertical grading, because this is a gravitationally driven process, you'll get larger class that are deposited first, and now these smaller class can fall through because there is no matrix supporting this particular depositional setup. On the other hand, for your type M fans, because you have a supporting matrix, there's nothing that can fall through, and the most gravitationally stable configuration will be the configuration that this class would take. So bigger class at the bottom, smaller ones at the top. So it's normal grading for type M fans. Next, I just need to review the question real quick. Yeah, so the next question asks you about the fabric of these class, right? Now you have a particularly snowy mountain, and these snowy mountains add moisture to the system, right? In this particular case, because of the snow that is being added to the system and the surrounding soil, of course, this entire mass of sediment, so there are these big class, these are supported by the matrix formed by the snow present in the surrounding regions. Now when this mass moves downhill, it's going to shear. And because of the shear force, you get a major axis and a minor axis. It's given in the rheology section. This is a particular kind of flow, and that is why you get an alignment. And the alignment will be, of course, along the direction of the flow. Now for the third part, which is the distinct patterns. Suppose you have a type M fan where there's a riverine deposit, right? The river flows in at a particular point, it deposits sediments there. Eventually, the sediments will build up. This is called a sandbar. Now, the sandbar will stop the flow of the river in that direction, and so the river would split and flow in a different direction. And that is why you get that pattern of markings in the particular fan. The last part of the question, yeah. Now for the last part of the question, the answer is simply multiple depositional events. You had a type P fan on top of which you had another type P fan deposited some point later in time. That's it. Any questions?
No questions? Thank you, Shivans.
So the final question of the evening is, I think this forest rotten right to the core. Nadli XCX, a scientist at the Society for Young Biologists and Advanced Understanding, recently came across a rather interesting forest in coastal and coastal adjacent regions around the world. Note, all locations mentioned in the question are located near the western region of North America and are situated near an active convergent plate boundary between the oceanic and continental lithospheric plates. These forests had varied vegetations. Some had cedars, some had casuarina, and others were straight up grasslands. But a common link, there were layers of dead forests beneath them. An example of a living plant and its dead counterpart are given below. The top image shows living marsh grass in a marshy gnarly forest, and the bottom image depicts a marsh grass buried under soil and fossilized in a gnarly forest. Question 1. In one such forest named Shub 6 in Alaska near the Cook Inlet, we find a land of short shrubs all around with sparse spruce trees. Gnarly decided to trench down near one such spruce tree and found a dead spruce stump named RA67 on top of which this new tree was growing. As they dug down, Narli found layers of deposits of silt surrounding the old spruce stump. The death of the stump itself was dated back to 1964. Much further inland, in a very marshy area, we see dead spruce stumps on the surface having age of death much later than 1964, but they are thought to be born at the same time. That is, they were part of the same forest at some point. What do you think could have led to the death of the older dated spruce? What led to the subsequent death of the inland trees belonging to the forest? Hint, an earthquake happened in Alaska around the same time in 1964. The first image depicts a cross-section of a trench dug near Bagwe 34. White line shows 1964 deposit. The second image depicts image of rings of the spruce stump beneath Bagwe 34. The leftmost point is the center, and we go radially outwards towards the right. Question 2. Gabriela, a scientist working with Narli, went to Willapa Bay near Washington. There she found a rather interesting pattern within the soils there. There was a thick layer of buried marshy soil full of humus, which was overlain by a 5 centimeter thick deposit of peculiar sandy soil, and on top of this sandy layer was subsequent tidal deposits. This sandy soil had an unusually high quantity of calcium carbonate and silica. Moreover, there were stones found in the buried marsh layer, which are typically not present at coastal estuaries like Willapa Bay. The soil between these layers shows almost a thin layer of transition between the two regimes. What could have led to this peculiar sand being deposited in this area? Why did this transition from marshy to tidal mud occur? This image depicts buried marsh soil with layers of sandy and marshy mixed, followed by tidal mud in the region of concern. Question 3. Game Boy RN at MIA, an organization that studies peats in Willapa Bay, collaborated with Gabriela to better understand the peculiar pattern of peats in the area. They produced a qualitative graph of the relative abundance of the two peat species, X and Y, in the region with an arbitrary time scale. Type X species have high fibrous roots and are darker due to on the What do you think could have led Do any of the participants have any doubts about the question?
One correction. In second,
Question 2.
Question 2, high quantity of calcium carbonate and silica.
Silica, yeah, it's supposed to be silica. Yeah, just make a note, it's supposed to be silica, not silicon.
In Alaska near the Cook Inlet.
Sorry, ask them the
Yeah,
question.
so it is in Alaska near the Cook Inlet. So does the word Cook Inlet have any significance here?
The word Cook Inlet.
Is it a certain geographical formation or something?
It isn't really relevant. All you really need to care about is the fact that these areas are located near a convergent plate boundary. Okay.
Okay, your thinking time starts now. You have 15 minutes. 10 minutes left. 5 minutes left. One minute remaining. Thirty seconds remaining. Time's up. I see you have 5 minutes to present. Your time starts now.
So the first question, as we know that it is mentioned that an earthquake happened in Alaska around the same time. So the earthquake of course can lead to the death of the older dated spurs, which was dated back to 1964. That's quite obvious. And now we know that the region is marshy, which means that it has a very high nutrient content soil, and of course it's a damp region. So it needs a high nutrient content soil. Since an earthquake happens and then followed by a tsunami, it might have wiped out some high nutrient content which is usually at the top, the more humus rich ones. The less humus rich ones will be left. Since the inland Mars plants require the more humus rich one, they will get less deficiency soil. So they won't die immediately, but due to the lack of nutrients, slowly and slowly they will die. And that is what the first part. They get swamped by tsunami, and the less nutrient one will just come on top. Since the top one has been replaced, means removed, and that's the answer to the first part. The lack of nutrient content is leading to death.
For the second part, we are theorizing, since it says that the sandy soil had a usually high quantity of calcium carbonate, we are theorizing that that sandy soil is of somewhat marine origin, because you would expect calcium carbonate deposits from marine animals in that region. So perhaps during the tsunami that have been caused after the earthquake, the sand from the ocean floor and potentially from the beaches in other area got deposited onto the grass and buried mass, and after that the rest of the things came, and that led to this particular situation. As that is for
For the third one, we know that Y is porous and lighter. So when there's an earthquake happening, there's also a tsunami. So the tsunami, after the earthquake, the tsunami washes away all the peat content. So the concentration decreases at that time. And for the first, X, it is more fibrous. So it requires a bit more like harsher conditions to form. So the earthquake provides those harsher conditions. So under this pressure and pressure conditions, it forms the X type of peat. So the concentration increases, and there is also a sudden dip after the formation. After a bit more time period. So that is not, yeah. So that is because of the tsunami, which also washes away a bit of the coal. So yeah, I don't know.
And for the second one, he just added that the ocean floor can come due to the tsunami, and basically this ocean floor, as we know, contains a rich source of calcium carbonate, and what is that? Calcium carbonate and silica. So the sandy soil which is there in the ocean floor usually can get deposited due to the tsunami event, and then later the tidal deposit which gets usually deposited after the tsunami can get on top of that, and so this peculiar sandy layer has been formed. That's it.
Short clarification for this part. We are saying that we are not saying that this is ophiolite. The oceanic crust has not gone on top of the continental crust. All has happened is a small layer of the sand that is there at the bottom of the ocean floor that has gone to the beach. That has gone to your
1 minute
forest.
left.
Do we have anything else? Make this better. Please. Fine.
thing.
30 seconds.
Just one more thing for the second, in the transition from marshy to tidal. I think I failed to mention that earlier. I believe the transition just occurred because of the tsunami happening, like the buried marsh soil being the original, like the original land or vegetation, and the tsunami bringing in mud and other sediments along with it, which led to the point.
Time's up. IIT Madras, you have 3 minutes to present. Your time starts now.
Hello. So for this question, the current location is given to be near an active convergent plate boundary between oceanic and continental lithospheric plates. And the first thing which we see is in figure 2, we are given a trench dug near Bagwe 34, which is a white line shown, which is the spot of the earthquake. So my claim would be that when the earthquake occurs, then earthquake occurs due to convergent plate tectonics, and so the trees in the ridge die. And for the argument to what led to the subsequent death of the inland trees belonging to the forest, that would be because of maybe the tsunami caused by it, or maybe because the ridge became a desert, and that's why a subsequent nutrient loss would happen to the inland trees, or there may be a possibility of a competition for the newly growing trees and the trees present earlier. For the second question, we have been given in the question that there are unusually high quantity of calcium carbonate and silica in between on the top of the marshy grass, which may be due to the felsic continental crust which came over the oceanic crust during the time of the earthquake. And after the earthquake, there is a divergent cycle also. So maybe the divergent is the reason for the death of the subsequent trees in the first part also. And then we are given that we have found rocks which are typically not present in at coastal estuaries. So that was the argument that the continental crust may have come over the while during the time of the earthquake. So that leads to the deposition given in this figure. And then for the third question, type X has high fibrous roots. For the third question, we have type X having high fibrous roots. The Y coordinates have the ratio, and the X coordinate has the year. So during the time of the earthquake, we can see that the ratio has significantly become 1. This may be due to the sudden death of type B species, which are earthquake prone due to them being spongy, porous, or rich in moss fragments. And then we can see that the growth still continues, and that may be due to two arguments. The first one being fast growth of moss, type B mosses, type Y, because maybe after the subsequent tsunami, the soil became nutrient rich for further growth B rather than type A. And the second argument will be the relative competition between types X and Y. Since the Y coordinates signifies the ratio, I believe that type Y has a competitive advantage of growth over type X in the same land.
There was one more observation, like in the figure 3, like the scales were like initially when it was close to the center, it was like more widely spaced, and as it goes away from the center, it was like.
Your time's up. IISER Bhopal, you have 2 minutes to present. Your time starts now.
Okay, so here subduction is happening. Due to that, earthquake occurs in 1964, which led to tsunami in the region. This tsunami brought a lot of silt deposits, or brought of deposits from the ocean to this region. This led to since because of nutrients loss and this led to instant death of this tree due to silt deposit and nutrients loss. This silt deposit, as we can see in the figure, is 10 centimeters. Also this tsunami created marshy lands here, further also reducing the nutrients value there, and therefore leading to death of the inland trees as well.
This is the subducting oceanic crust. This is the continental crust. So what happened was, initially there was mud because of the bay, the marshy area, and then the oceanic crust was deposited on this due to the subduction when the earthquake occurred. And then tsunami occurred due to the earthquake, and then the receding water, because the receding water carried all the silt and the mud back to the waters, which created another layer. and the transition happened because like some of the part of the oceanic crust became the part of the continental crust. So that is what.
Your time is up. IIT Delhi, you have 2 minutes to present. Your time starts now.
Okay, so for the first case, so we have two places here. So first we have to consider the fact that convergent boundary is being formed here. This is in the west coast of America. So it's in the Pacific and it's in the between stage 5 and 6 of Wilson cycle. And currently it's a converging plate boundary has been formed. So so the trees which are closer to the water bed that contained silt, and they are the ones that because of the earthquake went in here, and they instantly died in the 1964 earthquake. So these are the older ones, and the subsequent ones, basically because of the earthquake, a tsunami occurred, and it created a harsh environment within this forest region, especially in the marshy region, in the more inland areas, which were not affected by this, but were more inland. So those regions, because of the harsh
1 minute.
condition, the environment got choked, and they slowly got choked, and they couldn't survive.
Our claim for like the second and third parts is that basically you had the marsh soil, then you had a tsunami, after which it was covered with water for a while, which is when the 5 centimeter of transition came. And then because like that land had gone under, and there when the water receded, you started to have to come in on that patch of land only during the tides. So these are the three phases. Now I say that this is when the
30
tsunami came, and this is when it tide receded. And while the tides were still there and it was very saline, then it could not grow. But once the tides started coming in only for a little while, then our concentration of Y, it became feasible for it, and it reached a very low level of existence very fast when that tide thing happened, and there was some non-saline parts. Over time, Y grew because in general, in marshy areas, we know that Y naturally outcompetes X, and as the ocean receded more and more, it
Your time is up.
marshy.
Judges and question makers, do you have any questions for the teams?
Okay, IIT Delhi, so your reasoning for the tree death was that the trees go under the magma. Like, what was the reason why the trees were dying?
Yeah, so initially the trees that were closer to the tectonic plate boundary when they collided, because of the convergent plate boundary, they're the ones that died first because they went, yeah, they died first. And the subsequent, the ones that died later were because they got choked by the harsh conditions caused by the tsunami.
IIT Madras, how exactly does being spongy make type Y peat earthquake prone?
Like, I believe that type B, the sudden spike in the ratio was because type B died and so my guess is that type B is earthquake prone, and for to provide a reasoning I provided that type A, type X has thicker roots, so maybe they were able to sustain themselves, while type B, which were porous or had a mossy fragment, they died due to the sudden pressure of earthquake.
Okay. As there are no more questions, I'll call the question maker to explain the solution.
I am back. So again, going back to the participant brief, I mentioned a lot of things about time scales and space scales, and a lot of that is really useful here. The main takeaway I wanted from this question is for everyone to realize that, and I believe it was a little point in the participant brief as well, is that lithospheric plates are not completely rigid. They can deform, right? So now if you have a convergent plate boundary, I'll just use this diagram to set up a scale. This is in the order of meters, like vertical displacement, and this is in the order of kilometers, okay? Now, when you have this plate pushing into this plate, the material here, so this period of time where these two are pushing in together will be a very long time scale, right? When these two push together, the material here is going to pile up. And initially, you'll get a profile like this, right? There's a dip here. Now, because it is close to a coast, your water, ocean water, which is full of these salty, harsh nutrients, can flow in. And it's inside this bowl that the water will collect and kill all the spruce trees present in this region. Okay? Now what happens to this water later in time? It seeps into the soil in the region and spreads forward. This is a phenomena which is actually of great importance to people who work on biodiversity conservation. This leads to something called ghost forests. As this water percolates through the soil inland, it kills the trees later in time. So the initial killing event, so the initial death of the spruce trees happened because the water from the tsunami flowed into the bowl formed by the collection of land, and the later death happened because these nutrients, these harmful nutrients, percolated forward and killed the rest of the spruce trees inland. Okay. Now for the second part of the question, which dealt with the change in the soil type, was because when this subduction is happening, this is my oceanic lithosphere and this is my continental lithosphere. Basically, this entire piece of land is being pulled seaward, right? Now, if you're inside the continent somewhere and you're in a marshy environment, as you keep getting pulled out seaward, you'll turn into a more tidally driven environment. And that is why this change in soil had occurred. For the last portion, I believe most people had given me the right answer, which is that type X peats were favored by the harsher conditions, whereas type Y peats died out during these conditions. And in the normal scenarios, type Y peats outcompeted type X peats. Any questions?
Okay, so that concludes the deep thought round for ECS Mimamsa 2026. We thank everyone for attending this round. Mimamsa means will continue tomorrow with brief thought at 9 a.m. Just two announcements, I'm sorry. So please follow your team coordinators to dinner. And tomorrow for brief thought, please report at 8:30 a.m. to LHC 101.